Before we begin, tell me something quietly, just between us. What time is it where you are, and where in the world are you listening from tonight? Let me know in the comments below. I always read them. And if you're new here, gently, press subscribe before we start. Now close your eyes and drift with me. You don't see it, but it's everywhere. Floating between the stars, slipping silently through the vacuum. A substance so light it resists gravity's pull, and so small it drifts unnoticed through the vastness of space. It is not ash, not smoke, not sand, but something softer, older, what astronomers call interstellar dust. Tonight, let's begin with dust. Not the dust in your room or on your bookshelf, though that dust too tells stories, but the cosmic kind. The kind made in the bellies of dying stars, scattered across the universe in waves so gentle they drift for eons before settling in the arms of galaxies. For a long time, no one thought much of it. You see, the early astronomers, even the brilliant ones, were mostly concerned with light. Light from stars, light from comets, light from the sun. But dust got in the way. It dimmed the glow. It blurred the view. It was a nuisance, something to be subtracted or corrected for. In fact, when 19th century astronomers started noticing that certain parts of the sky looked strangely dark, black splotches across the band of the Milky Way, they didn't think dust. They thought gaps, voids, empty space. There was a man named Edward Emerson Barnard, quiet, patient, working with long photographic exposures at the Yerkes Observatory in Wisconsin. He was one of the first to suspect that these dark patches weren't holes in the universe, but something blocking the light. He stared for hours into the eyepiece of his telescope, then waited through longer hours for the glass photographic plates to develop. He didn't rush. He didn't speculate. He just observed, again and again. Year after year, the same portions of the sky on nights when the air was still and dry. When he published his work in 1919, a photographic atlas of these dark clouds, most of the scientific world still shrugged. The idea that there was anything in space besides stars and gas just seemed too odd. But Barnard was right. Those dark regions weren't empty at all. They were full of carbon, silicates, ices, tiny grains smaller than the width of a hair, formed in supernovae and stellar winds, billions of tons of it drifting slowly between stars, more ancient than any fossil, more common than any comet, and perhaps more important than anyone realized, because it wasn't just blocking light, it was changing it, filtering it, softening it, scattering the blue wavelengths and letting the reds pass through, like sunlight slipping through fog at dawn. Suddenly, astronomers had to question everything they'd measured: the brightness of a star, its color, its distance. Could dust be making the stars look redder? Could it be hiding entire galaxies behind a veil of shadow? But here's the strange part. Even though we know dust is everywhere, we still can't see it, not directly, not with human eyes. It took another kind of observer, someone willing to look not just at the stars, but between them, to make the next step. Someone who wasn't even born yet when Barnard died. A man who would spend most of his career waiting for light that had taken 100 million years to arrive. But how do you catch the faintest, coldest whispers of dust in a universe full of brighter things? And why would anyone spend a lifetime chasing what can't be seen? That's where we'll go next. The man's name was Frank Lowe. He wasn't looking for fame or applause or even clarity, really. What he wanted was quiet. The kind of quiet that only comes from the coldest parts of the universe. A soft silence that slips in just below what we can see. not in colors, but in heat, or more precisely in the lack of it. Frank Lowe was born in 1933. He studied physics, not the flashy kind with explosions and equations on blackboards, but the calm, meticulous physics of measurement. He became a specialist in cryogenics, the science of extreme cold, and in devices that could sense the tiniest temperature differences imaginable. By the late 1950s, he was working on infrared detectors, instruments that could pick up heat signals far beyond what the human eye could detect. Infrared light is like a whisper just beyond red, invisible to us, but filled with clues. And in space, where everything glows faintly from its own warmth, that whisper is constant. Now here's where it gets interesting. At the time, most astronomy was done in visible light. Telescopes were made for eyes, to magnify and capture what we could already see. But Frank wondered, what if some of the universe's best secrets were too cold to shine in visible light? What if they only glowed in infrared? And what if dust, that quiet, stubborn veil drifting between stars, wasn't just blocking light, but glowing softly itself? The problem, of course, was Earth. Our planet is warm, our atmosphere is thick. It radiates heat constantly. Trying to see cold things from a warm place is like trying to see candlelight from inside a furnace. So Frank did something odd. He put his infrared detectors on a telescope and then mounted that telescope onto a high-flying aircraft. Not a space telescope, not yet, just a plane. A converted military aircraft that could soar above most of Earth's heat and clouds. In 1965, he and his colleagues took off with their gear and pointed it toward the sky. What they found changed everything, because when you look at the universe in infrared, a kind of soft thermal vision, you see a completely different landscape. Stars that looked dim suddenly lit up. Clouds that seemed empty now glowed. And those dark regions Barnard had once photographed, they weren't black holes in the sky. They were alive with hidden heat, glowing faintly with energy trapped and re-emitted by dust. In other words, dust wasn't just a nuisance, it was a storyteller. It revealed places where stars were forming, still wrapped in cocoons of gas and debris. Places invisible to visible light telescopes, but warm enough to shine in infrared. Frank had opened a new window into the cosmos, and through that window we began to see the universe as a place not just of light, but of slow warmth. Lingering, in the dark. He didn't stop there. Over the next decades, Lowe helped design better detectors. He worked with NASA. He contributed to the design of IRAS, the infrared astronomical satellite, which in 1983 became the first mission to map the entire sky in infrared light. What it found was astounding. Whole galaxies hidden by dust, vast ribbons of matter stretching between stars, entire nurseries of stellar birth glowing quietly in wavelengths no one had seen before. It was like tuning an old radio to a station no one knew existed, and finding it was playing the oldest lullaby in the universe. But all of this depended on dust. Tiny particles, drifting gently through time and space, cooling, absorbing, re-radiating energy at just the right frequency for us to detect. Without dust, infrared astronomy would see nothing. Without dust, stars wouldn't form, at least not the way they do. Dust helps clump material together. It helps cool hot clouds so gravity can take over. It shapes how galaxies evolve and even how planets form. And yet, we still struggle to understand it. What is it made of, exactly? How does it form? How does it evolve? The answer depends on where you look. In some regions, cosmic dust is rich in carbon, built from the leftovers of old stars. In others, it contains silicates, tiny glassy minerals formed in the violent deaths of supernovae. Some grains carry frozen gases on their surfaces, some have been bombarded by cosmic rays, some have magnetic properties, others, strangely, don't, and all of them float, quietly, softly, changing the light of the universe just enough to make things appear redder, dimmer, further. For a long time, astronomers thought this reddening was a mistake, that it corrupted the data, but now they're starting to see it differently, because the way dust alters light tells us something important, not just about where the stars are, but what lies between them. And so the study of dust has become a kind of negative space. Science? You study what's missing to learn what's there. You look at how light bends, dims, and shifts, and from that, you reconstruct the quiet medium that caused it. Today we use space telescopes like the James Webb, which Frank Lowe helped conceptualize before he passed away in 2009. It orbits far from Earth's warmth. Its mirrors are gold-plated to better reflect infrared light. Its instruments are cryogenically cooled, just as Frank would have insisted. And still, it listens. To cold galaxies, to dusty clouds, to stars not yet born. But the more we look, the more questions we find. Where does the dust go? Does it survive forever? Or does it clump, collapse, transform? Why do some regions of space seem clearer than others? Why do some galaxies shine through while others vanish behind the veil? And maybe the softest question of all, if so much of the universe is shaped by what we can't see, then how much more is waiting quietly just beyond the light? The deeper astronomers looked into space, the more they began to realize something subtle and strange. That cosmic dust, once considered a nuisance, wasn't just interfering with our observations. It was defining them. Dust was no longer just the smudge on the telescope lens. It was part of the lens itself, not in a literal sense, but in the way it filtered the entire cosmic picture. The color of a galaxy, the brightness of a star, the temperature of a cloud. Each of these could be warped, quietly but significantly, by the invisible presence of dust. To measure the universe accurately, one had to account for that warp. To understand the stars, one had to understand what lay between them. In the late 20th century and early 21st, scientists like Eli Dweck and Bruce Drain began building complex models of dust behavior. These models weren't glamorous. They didn't capture the headlines or make the covers of glossy science magazines, but they were essential. Because only by simulating how dust absorbed and scattered light could astronomers correct their data. Only by knowing what dust was made of, its grain size, composition, temperature, could they understand what they were really seeing. And the data was astonishing. There were dusty galaxies so thick with interstellar particles that 90% of their visible light was blocked. There were entire populations of young stars completely hidden behind curtains of carbon. There were even galaxies, whole galaxies, completely missed by early surveys because they shone only in infrared. In a way, it was like discovering a new continent after already mapping the world. The visible universe was only a fraction of what was really out there. But here's something softer to think about. This dust, so quiet, so cold, it doesn't just shape what we see. It shapes what exists. Stars are born in dust clouds, not on their own, not in isolation, but in dusty nebulae where gravity slowly pulls material inward. As the cloud collapses, dust plays a secret role. It cools the gas, prevents it from bouncing away. It acts like insulation in a home, letting. The heat out slowly so the temperature doesn't rise too fast. Without dust, the gas might stay too warm. It might never collapse at all. And so, paradoxically, dust, the thing that hides light, also gives birth to the objects that produce it: stars, planets, moons, us. In fact, Earth itself is the product of dust. After the sun formed, a dusty disk remained, swirling, clumping, colliding, until pebbles became rocks, rocks became planetesimals, and eventually planets emerged. The dust didn't vanish. It just became part of something else. So if you look around your room right now, at the walls, your clothes, your own hands, you're seeing the final product of that process. You are, quite literally, the cooled and compacted dust of ancient stars. But the journey of dust doesn't end with planets. Some of it keeps drifting. There are grains of cosmic dust floating through our solar system right now, tiny flecks that entered our atmosphere over the past few days. Scientists call them micrometeorites, but they're not like the fiery meteors in movies. They're too small to cause fire. They simply fall unnoticed onto rooftops, lakes, forests, and sidewalks. If you placed a magnet on a paper plate after a rainstorm and gently collected the debris, you might pick up a few. And if you examined them under a microscope, you'd see something remarkable. They're round, perfectly round, spheres of glass fused by friction as they entered our atmosphere. They are travelers, ancient, silent, measuring just a few microns across, some of them older than the Earth itself. We are surrounded by them, and yet for most of history we didn't know. In 2016, scientists in Norway found micrometeorites on city rooftops, pristine particles that had fallen gently among the dust of modern life. Despite car exhaust, construction debris, and pollution, these spaceborne grains had survived intact. They were still falling just as they always had. It makes you wonder, doesn't it? How many things fall from the sky without anyone noticing? How many soft arrivals go unrecorded? Even today, despite our satellites and sensors, much of the dust remains invisible. We model it, we estimate it, but we rarely capture it in its rawest form. It's not that it hides from us, it's that we rarely know how to look. Some of the most interesting efforts to study cosmic dust now come not from grand observatories, but from gentle tools, balloons, high-altitude weather balloons, carrying detectors into the stratosphere, where they can scoop up dust before it mixes with Earth's own atmosphere. One project, called the Duster mission, has collected tiny grains thought to be older than our solar system. Each one contains clues about the chemistry of distant stars, stars that may have died billions of years ago. These are time capsules, not in vaults, not in glass cases, but floating freely. The sky is full of them. The ground is covered in them. They are the ash of creation, and somehow through them we begin to understand the colors of galaxies, because galaxies don't just glow white. They shimmer in blues, reds, yellows, and even purples, colors shaped not only by the stars they contain, but by the dust that filters their light. When astronomers use telescopes like ALMA, Spitzer, or Webb, they often create false color, images not to deceive but to reveal. Infrared is invisible to us, so colors are assigned to different wavelengths. Our glow at 100 microns might be shown as red, one at 60 microns orange, one at 20 yellow. And slowly, patiently, these images emerge, galaxies seen not in light, but in warmth, not in brightness, but in shadow, outlined by the dust that hides and reveals them at the same time. The colors we see are the colors dust allows. In a sense, dust curates the universe for us, not randomly, not cruelly, just quietly, gently. like a librarian choosing which pages to turn and which to leave for later. And so the man who waited for light, Frank Lowe, helped us learn to read those pages. Not with our eyes, but with instruments that could listen to the coldest notes. His legacy lives on in every dusty nebula we study, every warm speck we detect from a galaxy 10 billion light-years away, every hidden corner of the sky now softly glowing in false color. You may never see cosmic dust with your own eyes, but you see through it. Every night you look up at the stars. It's there in the redness of the sunset, in the pale glow of a nebula on a telescope image, in the long shadows that stretch across the Milky Way. And maybe that's the quietest lesson it offers, that what obscures also reveals, that the things we overlook shape the things we admire, and that even the smallest, softest, coldest particles can shape the color of a universe. Before the telescope, before the microscope, before even the lens, there was just glass. And long before glass was used for science, it was something else entirely, decorative, mystical, misunderstood. But in its still, transparent silence, glass has always had the power to bend light, to change what we see or what we think we see. This story begins not in a laboratory but on a beach, a stretch of ancient coastline, somewhere in Mesopotamia, or perhaps along the Egyptian shore. The precise location is debated, but the ingredients are the same: sand, soda ash, and fire. A common myth, and it is only that, a myth, tells of Phoenician traders cooking on the beach. Lacking stones for their cooking pots, they supposedly used blocks of natron from their cargo. When the heat of the fire fused the natron with the silica-rich sand, a glassy liquid pooled beneath the flames. It's a simple tale, likely apocryphal, but its core idea, and that glass began with fire and sand, is scientifically sound. Real glass-making, however, didn't begin by accident. In ancient Egypt, as far back as 1500 BCE, artisans were deliberately creating colored glass for beads, amulets, and tiny vessels, not transparent glass, not yet, but opaque, richly dyed materials. Deep blue from cobalt, turquoise from copper, amber from iron. Their aim was beauty, not optics. These glassmakers didn't know how to polish a lens. They weren't measuring the stars, but they were laying the groundwork, because every scientific lens, every microscope slide, every telescope mirror starts with molten sand, and this early glass was a puzzle. It wasn't easy to produce. It required temperatures above 1,000 tons, degrees Celsius, a careful mix of alkali and silica, controlled cooling to prevent cracking, and despite its ornamental intent, it responded to light in strange ways. Some scholars believe that ancient Egyptian and Mesopotamian artisans began to notice how thin glass fragments distorted the image behind them, how the sun shimmered through a shard, how the edge of a vessel made light ripple on the wall. Not understanding optics didn't mean ignoring them. These were visual cultures, keen observers of color and form, their religious ceremonies, their wall paintings, their gemstone. Carvings all relied on deep visual perception. It's likely that even if they couldn't articulate why light bent through glass, they recognized that it did. Centuries later, in Roman times, glassmaking evolved. Techniques improved. Transparent glass appeared. Windows were created, though, wavy and flawed. And somewhere, in a villa or a bathhouse or perhaps a temple, a piece of curved glass may have magnified a ray of sunlight just enough to burn a hole in fabric. Or light a priest's candle. These were not yet scientific tools, but they were clues. Fragments of Roman glass have been found across the empire, some with deliberate curves, some shaped like bowls, others like small spheres. In one famous example, the so-called Nimrud lens, a piece of ground rock crystal found in an Assyrian palace from the 7th century BCE, researchers still debate whether it was used decoratively as a magnifying aid or even as a primitive telescope. That debate matters less than the pattern it reveals, that long before science gave names to the behavior of light, refraction, diffraction, focal length, humans were seeing its effects, and slowly, patterns emerged. By the Islamic Golden Age, from the 8th to 14th centuries, glassmakers across Persia, Syria, and Egypt had refined their art. They created delicate vessels, shimmering with lusterware glazes, some of which contained silver, faint gold particles suspended in the glaze itself. This wasn't just beauty. It was early nanotechnology, manipulating matter at the microscopic scale to reflect light in precise ways. Meanwhile, scholars like Ibn al-Haytham were laying the foundation for optics as a science. In his book of optics, written in the 11th century, he challenged Greek theories of vision. Instead of assuming that the eye emitted light, he proposed that vision happened when light rays entered the eye, a radical shift at the time. To test his theories, Ibn al-Haytham used dark rooms, apertures, mirrors, and glass. He described experiments with lenses and refraction. He mapped the angle at which light bends when it moves from air into water and from air into glass. He even explored the concept of the camera obscura, a pinhole projection device that would one day lead to photography. And still, glass remained imperfect. The technology to grind lenses precisely, to mount them in tubes, to build telescopes, that wouldn't emerge for another few centuries, but the foundations were there in fire and sand, in lusterware and colored beads, in flawed window panes and shimmering vessels. The materials were waiting, the curiosity was stirring, and the stars above, they hadn't gone anywhere. It would take a long time before someone looked through the right piece of glass and realized they were seeing deeper than ever before. But what about the glassmakers themselves, the artisans who labored in the heat, who stirred molten silica with metal rods, who ground and polished for hours to create a vessel that might be smashed in a moment? Who were they? Their names are mostly forgotten. Rarely do the scientific journals mention them. They were not philosophers, not priests, not mathematicians, but without them, without their burns, their patience, their stubborn experimentation with materials, the optics revolution would never have happened. In a way, they were the first experimentalists, and perhaps on a quiet evening, as they held a finished piece up to the sun and watched the light curve just so, they saw more than they understood. So how did the art of glass, born in the furnaces of forgotten empires, become the eye through which we now observe galaxies? And what quiet, stubborn hands first learned to grind a perfect lens? Imagine a piece of glass no larger than a coin, polished just enough to be transparent, one side slightly curved, the other flat. In the hands of a tradesman, it might be a simple ornament, a pendant, a bead. But in the hands of a different kind of observer, a monk perhaps, or a clockmaker, it becomes something else, a lens. This is where the story shifts, slowly and almost without anyone noticing. By the late 13th century, lenses were being made and used regularly across parts of Europe. Not for astronomy, not yet, but for something more humble, reading. The first eyeglasses were likely developed in northern Italy, around the city of Pisa or Venice. These early spectacles were used by monks and scholars whose eyesight had faded. They weren't mass-produced, they weren't widely available, but they worked, not because of magic, but because of carefully curved glass, convex lenses. They magnified the written word, and that, in its own quiet way, changed the pace of thought. Now older scholars could continue reading. Scribes could write deeper into the night. Age, once a limit, became less of a barrier to study, all thanks to a few millimeters of curved glass. But still, no one thought to turn those lenses toward the sky. It would take another 2 centuries, and a shift in how tools were made, before lenses would reveal anything more than ink and parchment. The first recorded experiments with combining lenses in a tube come from the Netherlands in the early 17th century. A spectacle maker named Hans Lippershey is often credited with inventing the telescope, though records suggest others, including Jacob Metius and Zacharias Janssen, were working on similar designs around the same time. Their goal was not to explore the stars. They were simply trying to make things look closer. Ships at sea, perhaps, or distant buildings. These were spyglasses, practical tools, commercial innovations. And then Galileo Galilei got one. He didn't invent it, but he refined it, reground the lenses, pointed it not at boats, but at the heavens, and everything changed. In 1609, Galileo turned his telescope toward the moon. What he saw was not a perfect, smooth sphere, as many believed, but a rugged landscape of craters and ridges, shadows that changed with the phases. He drew them by hand using soft charcoal strokes and careful observation. He looked at Jupiter next, saw tiny stars beside it, and then, nights later, noticed those stars had moved. They weren't stars at all. They were moons, orbiting another planet. This was not just a technical discovery, it was a philosophical one, because for centuries the dominant worldview had placed Earth at the center of everything. The stars were fixed, the heavens perfect, the moon a flawless sphere. The idea that moons could orbit a planet other than Earth was quietly revolutionary. And yet, none of it would have happened without glass. The same material used in stained glass, windows in beads in perfume bottles, it had become, without fanfare, the conduit to another reality. Still, Galileo's telescope was crude by modern standards. The image was small, blurry at the edges, full of chromatic aberration, a rainbow halo caused by the lens bending different colors at different angles. But it was enough. Other scientists took note. Johannes Kepler, best known for his laws of planetary motion, wrote about improved lens arrangements. Isaac Newton, years later, would sidestep the problem of chromatic aberration entirely by inventing the reflecting telescope, using mirrors instead of glass lenses to focus light. But through it all, the central mystery remained. How does light behave when it passes through glass? This question wasn't trivial, because early glass was inconsistent. It had bubbles, streaks, impurities. Even when lenses were ground to the correct shape, the quality of the material itself could change how light moved. To truly master optics, scientists needed better glass, and for that they turned back to the artisans. In the 18th century, a man named George Ravenscroft in England began refining lead glass, what would later become known as crystal. It was clearer, more uniform, and more refractive than earlier glass. Initially used for decorative vases and drinking glasses, it also proved useful in optics. Around the same time in Bavaria, Joseph von Fraunhofer, a glassmaker turned physicist, began experimenting with producing uniform optical glass. He was meticulous, obsessed with precision. He created a glassworks where the entire process, from raw sand to polished lens, could be controlled. Fraunhofer didn't just make lenses. He made the tools to make lenses. And then he did something extraordinary. He pointed his telescope at the sun, not to look directly, but to analyze its light. Using a narrow slit and a glass prism, he spread the sunlight into a rainbow and observed something unexpected. Dark lines running through the spectrum. They weren't random. They were consistent, predictable. These lines, now called Fraunhofer lines, would later become the foundation of spectroscopy, the science of analyzing the composition of light. But at the time, they were simply strange, beautiful, unexplained, and once again glass was at the center. The prism, a triangle of transparent material, bent light in precise ways. The slit, a narrow opening, allowed only a thin beam to pass. Together they transformed light into data. Later scientists like Kirchhoff and Bunsen would use these principles to identify the elements present in stars: sodium, hydrogen, helium, all from the pattern of lines in their spectra. Suddenly, astronomy wasn't just about position and motion. It was about chemistry, composition, physics, and all of it depended on how light passed through glass. But there's something even more subtle here. Glass, for all its clarity, is also deceptive. It bends light, distorts it, slows it down, even. In the best lens there are imperfections, tiny warps, faint halos, edge blurs, so every image we see through a telescope is slightly altered. Every star, every galaxy, every faraway nebula, shown to us through something, and perhaps that's part of the magic, because glass doesn't just let us see further. It reminds us that all vision is filtered, that every observation, no matter how precise, carries the fingerprint of the tools we use. And those tools, they were made by people, people working in furnaces, people grinding glass under candlelight, people who never knew what their efforts would one day reveal. The history of optics is not just the history of scientists, it is the history of artisans, glassblowers, polishers, toolmakers, of hands burned by molten silica, of eyes strained by flickering light, and behind every discovery, from Galileo's moons to Fraunhofer's spectral lines, is the echo of those hands. So next time you look through a lens, a camera, a telescope, even a microscope, pause for a moment. Think of the people who shaped it. The sand melted, the curved surfaces ground by hand, the quiet understanding that light bends, and that through that bending, truth can emerge. But what happens when light passes through dust and glass? What do we really see when both the medium and the filter are changing the signal? And is it possible that some of what we think we know is still hidden just beneath the curve of a lens? At first glance, a telescope seems like a window to the stars, a portal cut through the sky, clean and smooth, connecting eye to cosmos. But look again. Every telescope is a compromise. Every lens, no matter how perfect, changes the light. It gathers, and the further that light has traveled, the more it has passed through clouds, atmospheres, gases, and dust. By the 19th century, optics had matured into a full-fledged science. Mathematicians could predict how lenses should bend light, and engineers could manufacture those lenses with precision never before possible. But as optical clarity increased, astronomers began noticing inconsistencies. A star viewed through, one part of the sky appeared dimmer than an identical star in another. Entire clusters seemed redder than expected. A pattern was emerging, one that refused to be corrected by better glass. It was cosmic dust again, now layered atop a new challenge. What happens when imperfect starlight enters a near-perfect telescope? This question wasn't a technicality. It was existential. If the instruments were becoming flawless, yet the data remained distorted, the problem wasn't the tool. It was the universe. And so, ironically, the rise of better optics exposed the need to study what couldn't be seen. But to understand that shift, we need to pause and look at the night sky from Earth. Picture yourself in a 19th century observatory. The dome creaks open. The air is still. A long tube of brass and glass points upward into the dark. You're watching the Milky Way, not as a blurry smear, but as a river of light. You adjust the focus. The stars sharpen, but between them, a strange darkness. Not just the absence of stars, a kind of textured blackness. It was through such a view that astronomers like Agnes Clerk and E. Barnard, both cautious, meticulous, began to argue that these dark regions were not empty sky, but veiled. Sky Agnes Clerk, a self-taught Irish astronomer and science writer, wrote prolifically about the nature of nebulae and interstellar space. Though she did not make direct observations, she brought attention to the increasingly detailed photographic surveys being taken by men like Barnard, and helped translate complex observations into ideas the broader scientific community could engage with. Barnard, meanwhile, used long photographic exposures to record the sky, not with the naked eye, but with early cameras. He noticed the same thing over and over. Light dimmed in certain regions, but the stars behind were still there. Fainter, redder, shifted. Something was muting their light. What he was seeing, and what Clark helped contextualize, was interstellar. Extinction, the process by which dust absorbs and scatters starlight. Not only was it real, it was shaping nearly everything astronomers had measured up to that point. Telescopes could bend and collect light, but if that light was filtered long before it reached the Earth, what exactly were they collecting? And still, despite this discovery, the tools kept improving. In the early 20th century, Carl Schwarzschild, yes, the same physicist whose name is now attached to black hole geometry, helped develop mathematical models to account for light absorption by interstellar dust. These models allowed astronomers to correct for the dimming effect, revealing the true brightness and therefore the true distance of stars. It was a breakthrough, but a humbling one, because it meant much of astronomy had to be recalculated. Distances, sizes, even star classifications, all had to be revised with dust in mind. The perfect lens could no longer guarantee a clear view. The clarity of a telescope was now entangled with the opacity of space itself, and this is where science and philosophy began to blur. For centuries, glass had represented vision, knowledge, enlightenment, but now it also revealed how little we could trust unfiltered sight. Even the most advanced telescope could only show what the universe allowed to be seen. And the universe, it turned out, was full of filters. But it wasn't discouraging. If anything, it opened up a new field of study: infrared astronomy. By the mid-20th century, astronomers began developing sensors that could detect not visible light, but the heat radiation of cold cosmic structures, often emitted by dust clouds themselves. Suddenly, things that had been invisible through traditional lenses were glowing. Dark nebulae became star-forming nurseries. Obscured galaxies emerged from behind curtains of dust. Whole regions of space, previously deemed empty, filled with quiet structure. And yet, even with these discoveries, dust still played tricks. One of the most curious was reddening, a phenomenon where light from distant stars appears shifted toward the red part of the spectrum. At first, this was confused with the Doppler effect, the red shift caused by objects moving away. But upon closer analysis, Scientists realize that dust itself preferentially scatters blue light and lets red light pass through. The result? A high star behind a dust cloud doesn't just look dimmer, it looks older or further than it really is, which means the universe might not be expanding as fast as we thought, or galaxies might be younger than they appear, or distances might be shorter. The implications ripple, and all because of a few grains of silicate and carbon floating in the interstellar dark. There's something poetic here. All our precision, our glass and our mirrors, our algorithms and detectors, and we're still limited by dust, not because we can't remove it, but because it belongs there. It's part of the story. We are not meant to look through a perfect, unfiltered sky. We are meant to learn from the veil. And so modern telescopes do not fight dust. They work with it, they listen in infrared, they adjust for extinction, they even map dust clouds, not as nuisances, but as structures, features of the landscape. The James Webb Space Telescope, for instance, carries this philosophy forward. Its gold-plated mirrors are optimized for infrared. Its sun shield blocks the warmth of Earth. Its instruments are cooled to near absolute zero, and when it stares into dusty regions, like the Pillars of Creation or the Carina Nebula, it does not see darkness. It sees birth. The very dust that hides the stars is where those stars are born. And that's the final gentle irony. For all our attempts to polish glass, perfect mirrors, and eliminate blur, some of the most important truths remain in the fuzzy regions, the veiled spaces, the muted light, not because we lack the tools, but because that's how the universe works. Stars emerge not from clarity, but from confusion, from chaos, from cold, from dusty, unstable clouds that collapse only when light can no longer escape. And so what we thought was obstruction was preparation, what we called noise, was signal, waiting to be heard differently. And the lens, polished to transparency, teaches us one final thing. That vision isn't about what we see. It's about how we see, with what understanding, through which filters, and with how much patience for the blur. Not all light is fast. Not all light is bright. There is a kind of light that prefers to whisper rather than shout. It hums through the cold, gliding softly between gas and dust, slipping out of reach of the human eye. This is infrared, not a color, not really, but a temperature. A warm breath of energy, felt more than seen, and in the vast, slow spaces between stars, this light is everywhere. Tonight we begin not with stars themselves, but with the darkness between them. The space that to early astronomers seemed empty. Void, utterly silent. But it isn't. It's filled with clouds, not the kind that drift across Earth's skies, but enormous, cold, quiet swaths of gas and dust. These molecular clouds, as they are called, span hundreds of light years. They are the coldest known natural places in the universe, with temperatures close to absolute zero, and yet somehow they glow, not with visible light, not with the bright, cheerful twinkling of stars. They glow in infrared, and long before humans could detect this strange warmth, it was already changing everything, shaping how galaxies formed, how stars ignited, how planets eventually came to be. So let's begin gently by thinking about what it means to see heat. Infrared radiation is simply electromagnetic energy with longer wavelengths than visible light. It's produced by all objects that have a temperature, from the faintest ember to your own skin, to distant nebulae cloaked in darkness. But it wasn't until 1800 that anyone discovered it. That honor goes to Sir William Herschel. Yes, the same Herschel who discovered Uranus. In a modest experiment, he passed sunlight through a glass prism, creating a rainbow on a table. Then, using thermometers placed at different positions in the spectrum, he noticed something peculiar. The thermometer placed just beyond the red, and where no visible light shone, recorded the highest temperature. There was something there, something warm, something invisible. He had discovered infrared, but the story didn't accelerate from there. It moved slowly, cautiously. For more than a century, infrared remained a curiosity, hard to measure, difficult to isolate. It wasn't until the development of infrared-sensitive materials and cooling techniques that scientists could begin to use it in astronomy. Why cooling? Because everything warm emits infrared radiation, including the instruments used to detect it. To truly sense the cold glows of distant space, telescopes had to be chilled, sometimes with liquid helium, down to just a few degrees above absolute zero. Only then could they listen. And what they found was surprising. The darkest parts of the sky were not empty. They were full of cold hydrogen gas, tangled magnetic fields, and interstellar dust, the remnants of ancient stars and the seeds of new ones. These cold galactic clouds were star factories. But they did not announce themselves with brilliance. They had to be observed over time, slowly, patiently, in wavelengths no human eye could detect. Early infrared observations were made from mountaintops: Mauna Kea in Hawaii, La Silla in Ciudad, Chile, where the air was dry enough to let some infrared light pass through. But eventually scientists realized they needed to leave Earth's atmosphere entirely. In 1983, NASA launched the Infrared Astronomical Satellite, IRAS. It surveyed the entire sky in infrared, and what it saw was breathtaking. Dusty galaxies hidden behind veils of gas, faint stars forming in cocoons, vast looping structures of material drifting through space like tendrils of smoke. Some of these regions had been observed before in visible light, but they made little sense. Only through infrared did their true nature emerge. The IRAS mission lasted less than a year, but it left behind a map that changed our understanding of the universe, and yet most of what it revealed had been right there all along. We had simply been blind to it. That's the strange thing about cold light. It hides not because it wants to, but because we were never designed to see it. Infrared astronomy, then, is not about building bigger telescopes. It's about learning to feel the quiet warmth of the coldest places. To understand this more deeply, consider the structure of a star-forming nebula. It begins as a cold cloud, dark in visible light. Inside it, slow turbulence stirs. Gravity whispers. Densities increase, and in one corner a pocket of material begins to collapse. Not violently, not quickly, just gradually, compressing under its own weight. As this protostar forms, it heats the dust around it, but not enough to create bright blue-white light. The temperature remains low, the glow remains soft. It's emitted in wavelengths that pass unnoticed through normal lenses. But through infrared detectors, these young stars shine like embers in fog. They reveal stages of stellar development that were once only guessed at. The dusty disks around them show signs of gaps, regions where planets may be forming. The surrounding cloud shows outflows, faint jets of gas shaped by newborn magnetic fields. All of this, invisible without infrared, and none of it hurried. The timescales here are immense. From cloud to star might take millions of years, from dust to planet, longer still. Infrared astronomy, then, is a science of patience. It does not deliver instant results. It rewards those who wait, And perhaps no one waited longer than the designers of the James Webb Space Telescope. The project began in the early 1990s. It was not launched until 2021. Decades of planning, failures, redesigns. Thousands of scientists and engineers, all to create a telescope so sensitive, so cold, so precise, that it could see the faintest glow from the first galaxies ever formed. Webb orbits far beyond Earth, at the L2 point, where the Sun and Earth's gravity balance. It stays in permanent shadow, protected by a 5-layer sun shield. Its instruments are cooled by cryogenic systems. Its mirrors are made of beryllium, coated in gold, optimized for the long wavelengths of deep infrared. Its key is in many ways not just a telescope, but a listener, a quiet ear, tuned to the soft music of cold things. And through it we've begun to see clouds. Again, not the bright ones of star catalogues, but the quiet ones, the filaments, the wisps, the overlooked structures winding through space like forgotten brushstrokes. Webb revealed galaxies so dusty they glow only in warmth. It showed the cause of nebulae once thought empty. It peered behind curtains of gas to see stars that had never been seen before. But it also reminded us we still don't know what we're missing, because every detection has a limit, and some warmth is still too faint, some clouds still too dense, some light still too cold. The universe does not give up all its secrets at once, and that in a way is comforting. It means there is still more to feel, more to listen for, more to learn by simply waiting. Infrared astronomy does not burst with spectacle. It does not announce its discoveries with dazzling explosions or vibrant celestial fireworks. Instead, it moves softly, steadily. It uncovers, rather than reveals. And what it uncovers, more often than not, is dust. But not dust as we know it, not the household kind, nor the soot that clings to chimneys. No, this is interstellar dust, fine and ancient, composed of carbon, silicon, and ices. Less than a micron wide, yet spanning light years in its collective form. This dust is what shapes the infrared universe, and in Section 2 we follow how this dust began to be mapped, not by sight, but by warmth. By the late 20th century, astronomers had begun to realize something profound. The Milky Way was threaded with filaments of cold material. These threads weren't visible in ordinary light, but they were warm enough to radiate in infrared. Not hot, just warm. A few dozen degrees above absolute zero. And when infrared-sensitive telescopes pointed to these regions, something extraordinary appeared. Structure. It began with IRAS, the infrared astronomical satellite launched in 1983. Though its mission lasted just 10 months, it scanned over 96% of the sky in infrared. IRAS didn't show points of light. It showed patterns, wisps, trails, endless threads of emission curling through what had once appeared to be black emptiness. These were the cirrus clouds of the galaxy. The term infrared cirrus was coined, not because of their composition, but because of how they looked. Thin, high-altitude threads like the delicate cirrus clouds of Earth's own sky. Except these structures were not kilometers above sea level. They were hundreds of light years wide, stretching across entire constellations. For the first time, humanity had a thermal map of the dust between stars. This changed everything. Suddenly, astronomers could trace where star formation might occur. They could see the boundaries of interstellar bubbles blown by ancient supernovae. They could follow how galactic magnetic fields aligned the dust, guiding its path like wind over sand dunes. And from this warmth, this quiet, glowing dust, a new kind of map emerged. A map of what wasn't visible, a map of what filtered. Light-cooled gas-shaped nebulae, but here's the subtle part. Infrared doesn't just help us see the dust, it helps us see through it when the wavelengths are long enough. That's because dust interacts differently with different kinds of light. Shorter wavelengths, like blue and ultraviolet, get scattered, but longer ones, especially those in the far infrared and sub-millimeter range, can pass through dust more freely. This allowed new telescopes like the Herschel Space Observatory, launched in 2009, to look into the densest clouds of the Galaxy. Herschel operated at far infrared and sub-millimeter wavelengths, and it saw cold material at just a few dozen Kelvin. Not blazing stars, not hot gas, just softly glowing dust. And what it found was incredible. Galactic clouds were not uniform. They were structured, filamentary, lumpy, dynamic, like tangled ropes drifting in water. Some filaments were dense enough to collapse and form stars. Others were merely highways of dust and gas, stirred by the gravity of passing stars, or shaped by magnetic turbulence. It was a kind of cosmic weather, slow, silent, and entirely invisible without infrared. But it wasn't just pretty. It carried information. By analyzing the light from these regions, scientists could estimate the mass of the dust, its temperature, even its grain size. With models, they could simulate how dust grains absorbed starlight and re-emitted it. They could guess how long it had been since a supernova exploded nearby, or how recently a burst of star formation occurred. Infrared became not just a way of seeing, but a way of reconstructing history. And sometimes it gave us glimpses of something even older. In 1998, astronomers using the COBE satellite made one of the most important detections in cosmology, the cosmic infrared background. This was not light from stars or dust in our galaxy, but a diffuse uniform warmth from far beyond. The accumulated infrared glow of all the galaxies, all the dust, all the processes of star formation across the entire observable universe. It was in the afterglow of ancient creation. Every photon in that glow had traveled billions of years, emitted by stars enshrouded in dust, scattered and rescattered, red-shifted by the expansion of space. And still it arrived. Even in silence, even after eons, the warmth remained. It is perhaps the gentlest evidence we have of the universe's past. Not a bang, not a flash, just a glow. Faint, persistent, real. And the more astronomers listened to this glow, the more they realized the universe has always been dusty. Even the first galaxies, even the first stars, the earliest structures formed in clouds thick with dust, and the light we receive from them now is filtered by that same material, stretched by time, made visible only through far infrared observation. And so through these observations, the oldest stars became the warmest shadows. But how do we keep listening? Modern telescopes like ALMA, the Atacama Large Millimeter Submillimeter Array, and James Webb have been designed to answer that question. They use vast arrays of detectors, placed in deserts and in orbit, to measure the faintest fluctuations in heat, changes of microkelvin, shifts in wavelength so small they barely register. They are not waiting for brilliant events. They are tuned to the everyday warmth of distant, dusty places, and through them we're building a new atlas, not of galaxies, but of the spaces between galaxies, not of stars, but of the cradles that birth them. It is a map of quietness, a map of dust and cold and time. And in this map, something beautiful happens. Places we once considered in the way, regions that blocked visible light, become foreground. They become data. They become central to the story, because the light that filters through dust tells us how much there is. The light that radiates from dust tells us where stars are forming, and the light that never gets through at all tells us what remains to be discovered. Infrared astronomy is not about peering further into space. It is about peering further into structure, into the nature of light itself, into how the universe stores and releases energy. Sometimes that energy comes in bursts, but more often it comes in warmth, a drifting ember, a glowing filament, a newborn star breathing heat into its nursery. And so the cold clouds of our galaxy, once overlooked, are now among the most closely studied structures in the universe. But what happens when we look beyond them? What is the infrared light that no galaxy can contain, the whisper of things older than dust, cooler than stars, and is it possible that the coldest places hold not just the past, but the blueprint of what comes next? There is a kind of light that never rises above a whisper. It moves slowly, not in speed, for all light travels fast, but in the way it carries information. It glides between dust grains over the quiet folds of space, never announcing itself, never forcing its presence. It is infrared light, the glow of what the universe is always doing, quietly, patiently, behind every bright flare and visible star. In this final part of our journey through cold clouds and ancient warmth, we turn to what this sleepy light is still teaching us, and what it might never fully reveal. Infrared astronomy has helped us understand how stars are born, how galaxies form, and how light filters through the fog of the universe. But it has also shown us something deeper, that the universe is layered, that we don't live in a clear, open cosmos, but in a space filled with slow sediment, particles and patterns that shape light long before it reaches us. And among the most mysterious of these structures are the cold cores. These are the densest, darkest pockets of molecular clouds, places where the temperature drops as low as 10 Kelvin, just a few degrees above absolute zero. No star shines within them yet. No visible glow escapes. They are in every sense invisible. But through sensitive far-infrared and sub-millimeter observations, scientists have begun to map these cold cores. Each one may be the seed of a future star, or of nothing at all. Some will collapse under gravity and ignite. Others will disperse, never becoming more than shadow. And here's the quiet mystery. We don't know which is which. We can't always tell, even with our best infrared tools, which clouds are stable and which are on the brink of collapse. The process happens over tens or hundreds of thousands of years, a blink cosmically, an eternity to us. This uncertainty isn't a failure. It's a lesson, because in astronomy, as in life, not everything is meant to be predicted. Infrared light, with its long wavelengths and patient rhythms, doesn't always show clear beginnings or endings. It reveals process, evolution, the in-between. It shows us the moment before a star is born, the last breath of a dying galaxy, the glow of dust that lingers long after the light source is gone. In some ways, it is the light of memory. Let's take a small detour now to the Large Magellanic Cloud, a satellite galaxy of our own Milky Way. It's visible from the southern hemisphere and has been studied in every wavelength imaginable. But in the early 2000s, when observed in the far infrared by telescopes like Spitzer and Herschel, it revealed something unexpected. Enormous reservoirs of cold dust, far more than predicted. This dust wasn't just left over. It was active. absorbing, radiating, participating in the galaxy's ecosystem. And in one region, the Tarantula Nebula, scientists saw hundreds of massive young stars, still wrapped in warm, glowing cocoons, lighting up the dust from within. These stars were invisible in the optical range, but in infrared, they stood out like lanterns under blankets, and it raised a question that still lingers today. How many stars in the universe are hidden in plain sight? Because if one galaxy, so close and well studied, could hide such complexity in warmth, then what of the others? What of the galaxies at the edge of visibility? What of the ones so far away? Their light has stretched into the far infrared or submillimeter, light we can only detect with specialized instruments, cooled to near zero, orbiting far from Earth's warmth. That's the job of telescopes like ALMA, which listens in radio and submillimeter wavelengths, and of the James Webb Space Telescope, with its unmatched infrared sensitivity. Together, they're helping scientists reconstruct the early universe, not from what is brightest, but from what is warmest, not from what stands out, but from what glows faintly, persistently at the edge of what we can detect. From this work has emerged a new kind of cosmology, not a universe of visible stars, but a universe of infrared structure, a universe where galaxies grow inside halos of cold gas, where dark matter shapes the scaffolding and dust outlines the walls, and within that scaffolding we begin to trace the path of light, not in a straight line, but in a weave, bending, scattering, delayed. Every photon we detect has a story, where it came from, what it passed through, what it became, and we are only beginning to listen. Here's something strange. The coldest objects in space can sometimes shine brighter in the far infrared than hotter objects in visible light. This is because of a principle known as blackbody, radiation, where even cold things radiate energy, just at longer wavelengths. A distant, dusty galaxy, so shrouded in its own debris that no light escapes, can still pour out warmth in the far infrared. And from that warmth, we can estimate its mass, its rate of star formation, even its distance. It's a quiet brilliance, one that requires patience, not just from the instruments, but from the scientists who study them. Because to work in infrared is to work in layers. Each image must be corrected for noise. From the telescope, the Earth, the cosmic background, each signal must be modeled, subtracted, compared. And still, sometimes what's left is nothing. Just a faint glow, a suggestion, a soft slope on a graph that says, something is here, but we don't know what. It might be a new star, or a dying one, or simply the echo of a galaxy's ancient dust. Infrared doesn't give answers, it gives clues, and that may be its greatest strength, because the universe isn't a machine waiting to be solved. It is a process, an ongoing exchange between energy and matter, dust and light, time and silence. And through infrared astronomy, we are allowed to witness that process, gently, without expectation, without demand, just warmth, just glow. And what lies ahead? Infrared astronomy is evolving. New missions are planned. NASA's Spherex telescope, set to launch in the near future, will scan the entire sky in near-infrared, creating a spectral map of over 100 million galaxies. It won't take pictures in the traditional sense. It will measure light signatures, tiny chemical fingerprints that tell us what each galaxy is made of. We will learn about water in planetary systems, about organic molecules floating in space, about how galaxies formed when the universe was still young, and all of it from warmth. But no matter how advanced the tools, some mysteries will remain. Some clouds are too cold, some stars too young, some signals too faint, and perhaps that's the beauty of it. Infrared light reminds us that science is not about conquering the unknown. It is about respecting it, approaching it with patience, with softness, with the understanding that not everything must be seen to be real. And so we end, not with an answer, but with a question. If the quietest regions of space are the ones shaping the stars, then what gentle forces might still be shaping us? What warmth, hidden, subtle, slow, guides our path through the dark? And what light are we still learning to see? You would think that by now we'd know what color the universe is. After all, we have telescopes that see billions of light years into the past. We've mapped radiation from the birth of time itself. We've catalogued stars, galaxies, clouds, filaments and fields in every possible wavelength, from X-ray to radio. But for most of human history, we didn't even think to ask the question, what is the color of the universe? The stars twinkle white. The night sky is black. Nebulae, if you've ever seen one through a telescope, appear faintly gray or greenish. And photographs, like those from the Hubble Space Telescope, show sweeping vistas of cosmic red, teal, and purple. But those images are not how the human eye would see them. They are filtered, color-enhanced, calibrated to extract meaning from invisible light. They are beautiful, but not literal. So in the late 1990s, a team of astronomers finally asked the question seriously. A straightforward, almost innocent query. If you gathered all the light from all the stars in all the high galaxies and combined it, what color would it be? Not artistically, not philosophically, scientifically. They weren't expecting controversy, but they got it anyway. The project started not with color, but with galaxies. Carl Glazebrook and Ivan Baldry, working with data from the 2DF galaxy redshift survey, were analyzing the light from more than 200,000 galaxies, one of the most comprehensive spectroscopic surveys at the time. They were focused on mapping the large-scale structure of the universe. But buried in the data was something else. The average spectrum of starlight. Each galaxy has its own mix of stars, hot and blue, cool and red, and everything in between. By averaging the spectral light from hundreds of thousands of them, the team could estimate what the combined light of the universe actually looked like. And when they processed the results, they found a color, not black, not gray, but turquoise, a pale blue-green, somewhere between mint and sea foam. They published the result in 2002. A few science writers picked it up. News outlets ran headlines like, "The universe is pale turquoise." It made people smile. It felt weirdly human, as if the cosmos had revealed a personal trait. But not long after, Baldry checked the code again, and there it was, a typo. Not in the data itself. The spectra were accurate, but in the color conversion algorithm, the part that transformed raw spectral energy into a perceptible RGB color for human eyes. Specifically, the algorithm had misapplied a correction for how human vision responds to different wavelengths. It was a small oversight, easy to make, hard to spot. When corrected, the result shifted. The universe, it turned out, was not turquoise, it was beige, a pale, warm, slightly off-white color, more cream than sky, more wheat than mint. Baldry called it cosmic latte, and just like that, the mood changed. Cosmic latte, not poetic, not bold, but as accurate. It was the average color of all the stars in all the galaxies, weighted by brightness and distribution, has blend of all the high-energy blues and low-energy reds, softened by time and filtered by space. The universe had spoken, and its message was, I am average, I am soft, I am warm. But what does that really mean? The color of the universe is not something we can see with the naked eye. No one standing on a mountaintop at night sees beige. So how can this be true? Let's pause and trace this carefully. Every star emits a spectrum of light. The hotter the star, the bluer its light. The cooler the star, the redder. Our Sun is roughly in the middle, a G-type main sequence star, and emits a spectrum that peaks in green. But because of the way our eyes blend colors, it looks white-yellow. Now, imagine summing up the light from all stars. The massive blue-white ones that burn fast and die young. The tiny red dwarfs that will outlive the galaxies themselves. The glowing remnants of past generations, and the new stars just coming into being. Now add the effect of dust, reddening the light, absorbing and re-emitting it in the infrared. Now, apply redshift, the stretching of light as space itself expands, shifting spectra toward longer wavelengths. All of this contributes to the average color of the universe, and when you do the math correctly, you get a color temperature of about 4,800 Kelvin, corresponding to that pale beige. Not exciting. Not cosmic purple or galactic blue or nebular crimson, just soft white, and in that quiet result lies a larger truth. The universe is not young. Its average stars are not newborns. The blue giants of the early cosmos have mostly burned out. What remains are midlife stars, old clusters, long-burning dwarfs. The universe, in other words, is aging, and its color reflects that. If we had asked the same question 10 billion years ago, the answer would have been different. The universe would have been bluer, hotter, more youthful, its galaxies packed with energetic stars and violent formation. But now things have calmed. The star formation rate has slowed, the light has softened, and so, beige, cosmic latte. There's something poetic about the mistake, the initial announcement that the universe was turquoise. It captured the imagination. It felt special, unique, but the correction, the beige, was the real beauty. Because it reminded us that science is not just about discoveries. It's about refinement, about humility, about checking the code, correcting the algorithm, adjusting the lens, literally and figuratively, and in doing so, we came closer to the truth, even if that truth was quietly unremarkable. But this isn't the end of the story. Because if the universe is beige today, what will it be tomorrow? The answer lies in stellar evolution. Over the next trillions of years, yes, trillions, star formation will continue to decline. The massive hot stars will vanish first. The cool red dwarfs will persist, growing even cooler. Eventually, all that remains will be fading embers, white dwarfs cooling into black dwarfs, theoretical objects so cold they emit almost no light at all. The universe's average color will shift, slowly, from beige to red to infrared to darkness. There will be no more visible light, only heat, only the long, slow exhalation of matter as it settles into equilibrium. This is not catastrophic. It is not an explosion nor an ending. It is a cooling, a settling, a sleep. And in that sleep, the light that once lit galaxies will still be there, not gone, but stretched, faint, long, quiet. Infrared. Once again, infrared. The same warmth that glows from newborn stars today will be all that remains in the far future. And so perhaps we return to the theme of this series, that the coldest light is the most enduring. Infrared may not dazzle, it may not cast shadows, but it persists. It threads between dust grains. It endures through cosmic time. It outlasts brightness. It is the final voice of the universe. And maybe in some distant time, when intelligent life, if any, evolves again and looks upward, they won't see stars at all, they will listen. And what they will hear is warmth, a background hum, the afterglow of galaxies long gone, still whispering across the darkness. So the next time someone asks you what color the universe is, you can say, it's beige, it's aging, it's honest. Or maybe you can say it's the color of memory, the color of a light that used to shine, a light that still travels, and a story still unfolding. The universe doesn't come with a color label, and even when we assign it one, the result is conditional, subjective, dependent not just on what the light is, but on who or what is doing the looking. In Section 1, we traced the quiet comedy of the cosmic color typo, how a tiny coding mistake turned the universe turquoise, only to be later corrected to a more modest beige cosmic latte. A small error, easily overlooked, but it revealed something profound about astronomy itself. Color is not a thing we discover. It's a thing we construct, and this idea becomes even more slippery and sleepier the more deeply we think about it, because color in astronomy is always an illusion. Not a lie exactly, but a soft interpretation, a whisper of meaning wrapped in translation, from raw photons to electrical signals, from wavelengths to pixel values, from graphs to images. Tonight, in this next part of our journey, we rest our attention on the question, how do we decide what the universe looks like when none of our tools can see it directly? Let's begin where color begins, with light. Every beam of light is composed of a range of wavelengths. The shortest, gamma rays and X-rays, are extremely energetic and invisible. Then come ultraviolet, visible light, infrared, microwave, and radio, each less energetic, longer in wavelength, quieter in tone. The human eye is tuned to a small sliver in the middle, the visible spectrum, between roughly 400 and 700 nanometers. Violet to red, this narrow range shaped everything. Our vision, our art, our early science. But most of the universe shines outside of it. Infrared, we can't see it. Ultraviolet, we can't see that either. X-rays, radio, gamma rays, all invisible, and yet modern astronomy is built on these invisible forms of light. So what do? We translate. We assign colors, often arbitrarily, sometimes strategically, to different wavelengths. We take an infrared signal and render it red. A shorter infrared may be orange, a very short infrared, perhaps yellow. We do the same with X-rays, assigning false colors to energies we cannot perceive. And from this translation, a picture emerges. The Hubble Space Telescope, for instance, often captures light through specific narrow filters. One tuned to hydrogen alpha, red, another to oxygen 3, green-blue, another to sulfur 2, deep red. The raw images are black and white, intensity maps, but astronomers then assign RGB values to each filter. The result? Nebulae that glow with eerie green wisps, magenta cores, cyan tendrils, galaxies painted with golden arms and teal halos, fields of stars dappled in blue and orange. Are these colors real? No, and yes, they are representative. They illustrate differences in temperature, chemical composition, density. They tell a story, a visual metaphor for what can't be seen. Directly, but they are also choices made by scientists, by algorithms, by editorial judgment. Even the now famous Pillars of Creation image, that sweeping Hubble photograph of towering dust clouds in the Eagle Nebula, is not how the human eye would see it. The real view through an eyepiece would be pale, dim, grey-green at best, but Hubble saw through filters, and scientists painted the scene accordingly. So again, we return to the idea that seeing the universe means building a version of it, a version shaped by our tools, our models, and our visual expectations. And that brings us back to telescopes, because telescopes don't see color. They collect photons. Whether it's a mirror or a lens, a CCD or a cryogenic bolometer, the job of a telescope is to gather light and measure its intensity. How many photons arrive, at what energy, from which direction? From these raw counts, scientists reconstruct spectra, graphs of energy versus wavelength. Only later, much later, do colors enter the picture, and even then, there's more complication. Let's say we're observing a galaxy 10 billion light-years away. Its light has traveled across a universe that is expanding. That means the wavelengths have been redshifted, stretched into longer, slower forms. A bright blue star in that galaxy may now appear yellow, or red, or even infrared. So what's the true color of the galaxy? Is it what it looked like when the light was emitted? Is it what it looks like now? Is it what our instruments detect, or what our processing software reconstructs? The answer depends on your goal. For a cosmologist measuring redshift, the color is a tool. For an outreach specialist building an image for the public, the color is a story, and both are valid. Because the point isn't accuracy, it's understanding. Color is a translator, a bridge. And in astronomy it is often a bridge between meaning and mystery. But if all this seems messy, if it feels as though we're just guessing, take heart. There is precision beneath the art. For every beautiful image there are calibrations. Each filter has a known response. Each detector has a noise model. Each exposure is timed. Every color decision can be traced to a measurement, a wavelength, a temperature, an elemental signature. It's not that the colors are arbitrary, it's that they are interpretive. They carry data. The red glow of a hydrogen cloud reveals a region of star formation. The blue tint of a stellar halo may indicate young, hot stars. The yellow-orange core of a galaxy reflects older, cooler populations. So even in their artistry, these images remain rooted in reality. And the average color of the universe, that quiet, unassuming cosmic latte, remains perhaps the most honest of all. Not because it's dramatic, but because it was measured from real spectra, real stars, real galaxies. It is the color of the night sky, summed over time and space and silence. There's one more wrinkle to explore. Us. Human eyes are not the same across cultures, ages, or individuals. Color perception is influenced by biology, context, memory. What you call blue may not match another person's experience of blue. And across species, the differences are profound. Bees see ultraviolet. Snakes sense infrared. Birds see more colors than we can imagine. So whose version of the universe is correct? The answer is none and all. Because color is not a property of light. It is a reaction to light. A relationship between signal and sensor. And in astronomy, the sensor is always a tool, never the truth itself. So when we ask, what does the universe look like? We must also ask, to whom? With what eyes? Through what filter, through what lens, and with what expectation? And perhaps the softest, sleepiest answer is this. The universe does not mind what color we give, yet it glows anyway. In wavelengths we cannot see, in patterns we cannot name. But if we choose to assign a color, to map the light into latte or turquoise or rose, then we are not seeing the universe. We are seeing ourselves reflected in our instruments, our yearning for clarity, our need to paint the void. And that is beautiful. Because the color of the universe in the end is not a measurement. It is a conversation between light and glass, between dust and algorithm, between wonder and warmth. It's odd to think that light, something that moves at the fastest known speed in the universe, is often the slowest thing to understand. It takes just over 8 minutes for sunlight to reach Earth, but it took humanity thousands of years to understand what sunlight even was. We studied shadows before we studied photons. We watched eclipses before we watched spectra. And when we finally learned to measure the light of distant galaxies, we still had to translate it, question it, decode it, and sometimes mistranslate it entirely, as in the accidental turquoise of the cosmos. But now here we are, with computers, color maps, filters, telescopes the size of buildings, and we still don't know what light looks like without us. In this final section we settle into that uncertainty. The soft, slow kind, the kind of thinking that doesn't need to resolve into clarity, the kind of wondering that's good for drifting off to sleep, because, as it turns out, the color of the universe is not just a curiosity, it's a reminder of how we see, of how everything we measure is filtered, not just by cosmic dust or glass lenses, but by us. And maybe the best way to understand the color of the universe is to stop trying to see it, and instead learn how to listen to light. We left off with cosmic latte, that now famous beige derived from the spectral average of over 200,000 galaxies. A warm white, not dazzling, not dramatic, but honest. Statistically, complete. The universe boiled down to a spoonful of light. Let's stay with that image for a moment. Imagine a spoon filled with photons. Not real ones, of course. Light doesn't gather that way, but figuratively. A spoon that holds the average light emitted by every star, planet, and glowing gas cloud in the known universe. In that light are traces of hydrogen and helium, of iron forged in stars, of oxygen drifting in nebulae. Each element bending the spectrum just slightly, absorbing a sliver here, emitting a line there. Each tweak, invisible on its own, adds up to a broader shape, a fingerprint of everything the universe has done with its energy over the last 13.8 billion years. And when you mix it all together, the sum total of those wavelengths forms. Beige, but why does that matter? Because light is history. When we look at light, we're looking at time. The further away something is, the longer its light has traveled to reach us. The deeper the redshift, the older the message. So when we calculate the average color of the universe, we're not describing the light as it is now. We're averaging light that started its journey billions of years ago. That color isn't a snapshot. It's a story. A weighted blend of ancient heat and quiet cooling, and that story is always changing. As we look at younger and younger galaxies, further and further into the past, we find that they're bluer, more energetic, full of hot, massive stars that burn quickly and die young. As we look at closer galaxies, more recent times, we see redder light emitted by older stars with longer, cooler lives. If we could color code time itself, it would run from blue to red, from early fire to late fading, but we never see it all at once. Our view of the universe is patchy. It's stitched together from different telescopes, different filters, different instruments. No one telescope sees everything. Each one gives vars a piece, so even the average color of the universe is not a fundamental property. It's a calculated agreement between wavelengths, a harmony of incomplete melodies. And yet, it's real, because even if the music is never heard all, at once the tune still exists. Now let's look down, not up, and think about the role of instruments. Every telescope has a bias. Some are tuned for visible light. Others specialize in infrared X-rays or gamma rays. Some are placed high on mountaintops to avoid moisture. Others orbit in space to escape the blur of Earth's atmosphere. And each one builds a different picture of the same universe. This isn't a flaw. It's a strength. It means that no single image, not even a high-definition photograph from Hubble or Webb, is the whole story. Every image is a composite, a selection, a translation. Colors are assigned based on filter bands, slices, of the electromagnetic spectrum that pass through specific instruments. A red filter might correspond to hydrogen alpha emission, a blue filter to oxygen lines. A green filter might be synthetic, interpolated to help the image look natural. But these colors aren't literal. They are mnemonics, visual cues, a way to hold data in your memory. An image of a galaxy with blue arms and a yellow center tells you something useful. The arms contain younger, hotter stars, while the core is full of older, cooler ones. But it does not tell you what the galaxy looks like, because space has no ambient light, no blue sky, no surrounding color context. If you were floating near that galaxy, you'd see a dark void with faint smudges of light, pale, colorless, blinking dimly in all directions. The color comes after. The color is added by us to organize the chaos. And then there's redshift, that slow stretching of light caused by the expansion of space itself. Every distant galaxy is moving away from us. The further away it is, the faster it recedes. And as it recedes, its light is stretched, redshifted, to longer wavelengths. A galaxy that once glowed in ultraviolet may now appear red, or even infrared. A supernova that burned with blue-white fury might now be a warm ripple on a deep spectrum chart. So again, we return to the question, what color is the universe? The answer is, it depends where you're standing. It depends what your instruments are tuned to. It depends when you're asking. The cosmic latte we calculated is only true from here now, from Earth, using our instruments, looking at the light that has just reached us after traveling for eons. If you were on another planet, in another galaxy, 10 billion years ago, your answer would be different. Maybe it would be bluer. Maybe there would be no beige yet. Maybe the galaxies were still too young to soften. Color, then, is not a destination. It's a phase. And the universe has gone through many. The earliest phase, before stars, was all infrared. A soft afterglow from the Big Bang, slowly cooling into the cosmic microwave background. That glow still surrounds us. It fills the universe. But it is invisible. We detect it as a 2.7 Kelvin signal, uniform in all directions. No color, just warmth. And now, in our current phase, the universe is beige. In the future, it will redden further, drift into infrared, slide toward darkness, as stars burn. Out light will lengthen, wavelengths will stretch, color will fade. And in the end, the universe may not have a color at all. It may become colorless. Not black, but colorless in the strictest sense, because color is defined by contrast. And in a universe without stars, without gradients, without heat, there is no contrast, no perception, only silence. But even that is beautiful, because it reminds us of the fragility of perception. The color of the universe is not a feature of space. It's a reflection of where we are in time. Right now, in this moment, the cosmos glows with enough stars, enough contrast, enough visible structure for us to calculate a color. A soft one, a pale one, beige, cosmic latte. Not the color of energy. Not the color of youth, but the color of balance. A middle tone somewhere between fire and ash, between birth and rest. And maybe that's the best time to be alive, when the light is still visible, but not blinding. When the universe is old enough to be knowable, but not so old that it's fallen asleep completely, maybe the beige of the cosmos is not boring. Maybe it's perfect, because it's the only time when we can look up and build a picture and a sign, a name to the light that surrounds us, even if that name comes after a typo, a recalculation, a gentle moment of humility. So let the final thought be this: we do not live in a blue universe. We do not live in a red universe. We live in the space between, a brief beige eternity, a soft middle note in a long, slow song. And even if we can't hear the whole melody, we can hum the part that reaches us. You could stand with another person under the same sky and look at the same star, but you would not see the exact same thing. You might see it as white. They might see it as yellow or blue. You might both point and agree that it twinkles, that it looks a little fainter tonight. But the truth is, the light of that star has traveled across unimaginable distances, through dust, gas, magnetic fields, and time, and by the moment it reaches your eyes, it has already changed, and not just once. Many times. The star did not change, but its light did, shaped not only by what it passed through, but by how you receive it, by the air around you, the clarity of your eye, the kind of telescope you use, the color receptors in your own biology. The colors of stars are not a universal truth. They are a conversation between light, matter, and perception. This final story is about those quiet conversations. It's about how dusty stars tell different stories to different observers, and how the universe we see is, in many ways, a filtered version of the universe that is. Let's begin, not in the present, but in the 1800s. At a small observatory in Germany, an astronomer named Friedrich Wilhelm Bessel was studying the apparent motions of stars. Among them, he noted something odd about a faint star called 61 Cygni. Its position shifted more than others as Earth moved through its orbit. This wasn't a mystery. It was the result of parallax, the apparent motion of nearby stars against a more distant background. But it reminded astronomers that stars aren't static, nor are their colors fixed in place. At the time, stars were broadly categorized by brightness and position. Color, if noted at all, was a secondary curiosity. Observers often describe stars as reddish or bluish by eye, but no standard system existed. That began to change when spectroscopy emerged. As we touched on earlier, spectroscopy is the science of separating light into its component wavelengths, creating a kind of rainbow, or more accurately, a spectrum. When starlight is passed through a prism or diffraction grating, it spreads into bands of color, each with tiny dark lines. These absorption lines correspond to elements in the star's atmosphere, hydrogen, calcium, iron, and more. But the shape of the spectrum, how bright it is at each wavelength, tells us the star's temperature. Hot stars glow mostly in the ultraviolet and blue. Cool stars glow more in the red and infrared. And so the color of a star became a scientific quantity, not just a visual impression. Still, this did not solve the problem of dust. Dust, that fine interstellar veil, scatters short wavelengths like blue and violet more strongly than it does red. This means that as light from a star travels through dusty regions of space, it becomes redder than it originally was. This process is called interstellar reddening, and it's why some stars appear orange or red even when they are, in fact, white or blue. To an astronomer looking with the naked eye, the star might seem cool, old, distant. But to a telescope that can analyze the star's full spectrum, or better still, detect its light in infrared, which passes more easily through dust, a very different story emerges. In this way, dusty stars whisper different truths, depending on who, Galaxies or what is listening, but the differences don't stop there. Even two modern telescopes may not agree on a star's color. Why? Because detectors have personalities too. A CCD sensor in an optical telescope is more sensitive to certain colors than others. It might underemphasize red light or overemphasize green. A space telescope like Hubble uses filters, red, green, blue, to build composite images. But the final colors are approximations, not absolute truths. Wavelengths outside the visible. Range, in ultraviolet or infrared, must be mapped to false colors. This means assigning a color we can see to a wavelength we cannot. And yet, these choices, necessary as they are, shape our emotional and scientific perception of what we're seeing. A nebula shown in magenta might evoke mystery. In green, it might seem toxic. In blue, serene. But these impressions come not from the nebula itself, but from our translation of its invisible voice. And that brings us to one of the quietest realizations in astronomy. There is no such thing as a true color image of space. Not because the images are fakes, they're not, but because color itself is not a fixed property. It's a relationship between a source, a filter, and a receiver. Let's bring this closer to home. Think of the sun. It looks yellow, right? And yet, its spectrum peaks in green. So why doesn't it look green? Because our eyes and brains combine all the wavelengths it emits and interpret them as white-yellow. The atmosphere scatters the blue. Pollution or humidity shifts its tint. At sunrise and sunset, it turns red. Not because the sun changed, but because the path through the atmosphere increased. The sun, too, tells a different story depending on who is listening and how. Astronauts in space report seeing it as a blinding white. On Earth, it is often golden. Through a telescope with a hydrogen alpha filter, it becomes blood red, revealing flares, prominences, magnetic arcs. It is the same star. But each observer hears a different whisper. Now scale that concept back to distant stars, to ones 10,000 or 100 million light-years away. Add in redshift, the stretching of light as the universe expands. Add in atmospheric absorption, lens, coatings, sensor calibration, even the color profile of your computer screen, and you begin to realize every image of space you've ever seen is personal. It is shaped by the instruments, the processing, the intent of the people who prepared it. And that's not a flaw. It's a reminder that science, for all its rigor, is still a collaboration between reality and perception. Even the stars don't speak in absolutes. One of the most touching examples of this comes from a lesser-known mission, the Infrared Space Observatory, ISO. Launched in 1995 by the European Space Agency, ISO observed dusty regions of space in mid and far infrared, wavelengths entirely invisible to the human eye. When its data was first published, it showed glowing tendrils of gas, spirals of warm, dust, disks of planet formation, none of which had ever been seen before. But when astronomers presented these images to the public, they had to choose colors. They assigned red to longer wavelengths, blue to shorter ones, green somewhere in the middle. The result was surreal, not because it was wrong, but because it reminded us that color in this context is a language we create to understand what cannot be seen. And the dusty stars in those images? They became luminous, no longer hidden. Their whispers had been translated into warmth, shape, color, and so a star that once glowed unseen behind a thick cloud could now be heard, not in brightness, but in tone. So why do dusty stars whisper different colors to different eyes? Because each of us, astronomer, telescope, detector, human viewer, is not a passive observer. We are participants in perception. The light comes from far away, yes. It travels undisturbed, yes. But when it arrives, it enters a context, a receiver, a framework, the same light, different story. And that means something. It means the universe isn't just out there. It's between us. In the act of seeing, we shape what is seen. In the act of listening, we influence the song. And in a cosmos filled with light shaped by dust, that influence is profound, because what we call seeing is really feeling, with tools, with calibration, with care. As we end this fifth and final story, let's return to one last image, a dusty star, seen through a veil. Its light faint, reddened, barely arriving. It travels across trillions of miles. It passes through clouds, through time, through space, and then it enters your eye, and what you see is not the star, not exactly. You see its conversation with the universe and with you. By the time light from a distant star reaches your eye or telescope, it has already lived a life of its own. It has been born not from the surface of the star itself, but from layers within it, bubbling outward, scattering, bouncing, compressing, refracting through stellar gases, leaking finally into space. It escapes not as a shout, but as a quiet stream, and then it begins its journey. Tonight, we'll follow that light on its slow path, not to understand how it travels in a straight line, but how it changes, how it becomes something else, how it becomes a kind of ghost, shaped by what it has passed through. We begin deep inside a dusty star. Not all stars are dusty, but many are surrounded by clouds of their own making, the aftermath of ejected material, burned off layers, outflows and winds. As stars age, they swell. They lose mass, they become surrounded by gas and dust, carbon-rich, silicon-rich, or in some cases, exotic minerals like corundum and spinel. The dust doesn't stay. Still it moves. It forms shells. It reflects some starlight and absorbs the rest, re-radiating it not in the same color, not even in the same type of light, but in infrared. So the first filter in a dusty star's whisper is the dust the star itself produces. This alone can alter its perceived color dramatically. A carbon star might have once shone brightly in red-orange visible light, but now enshrouded by dust it radiates mostly in the infrared. A human eye wouldn't see it at all. To us it looks faint, dim, cold, but it's not. It's still burning, just softly. Now the light leaves the star's immediate cocoon, but space is not empty. Between stars lie interstellar dust clouds, vast and tangled, made of the leftover fragments of older generations of stars. This is the dust of galactic arms, of nebulae, of molecular filaments. It is microscopic, but its influence is vast. Some dust grains are small enough to interact with ultraviolet light. Others affect visible wavelengths. Together, they act like a fog, scattering short-wavelength blue and violet light, allowing red and infrared to pass more freely. This is where the reddening begins. It's subtle at first. A blue-white star behind a light dust cloud might look ivory, like an old photograph left in the sun. Add more dust. The ivory turns gold, still more. It looks orange. At some point it fades completely from the visible range. Only the infrared remains, but the star didn't change. Only the path of its light did. And the longer the path, the more dust between you and the source, the more the whisper is altered. This process is called interstellar extinction, and it doesn't just dim the star's light, it changes the very spectrum of what arrives. And that's why no two observers may see the same star in the same way. A telescope in Hawaii, looking at a star low in the atmosphere, sees a red-shifted, hazy version. Another telescope, orbiting in space, bypasses the air entirely and sees a much bluer, crisper view. A telescope in Chile, operating in infrared, sees the glow from the star's dust, not the star itself. Each tool collects a different part of the story. Each one listens to a different voice from the same object. This raises a fascinating question. If no observer ever hears the same whisper in quite the same way, can we ever really know what the star truly looks like? This isn't just poetic, it's scientific, because the tools we build, telescopes, spectrometers, cameras, all have limits. They are sensitive to certain wavelengths and blind to others. They have calibration curves, sensitivity drops, thermal noise. Even our eyes, those ancient organic detectors, have their quirks. We are less sensitive to red at night. We process green more efficiently. Our peripheral vision sees motion better than detail. Our rods and cones, the cells in our retina, interpret color differently, depending on intensity. So when we see a star, we are not seeing what it is. We are seeing what we are capable of seeing. And when our instruments observe a star, they are doing the same, filtered by technology, calibration, software. So again, the light becomes a conversation, not a fact. This becomes even more complicated with variable stars. Some stars change brightness, not because of dust, but because of intrinsic changes in their structure. Take Mira, one of the most famous variable stars in the night sky. Mira brightens and dims. Over months, its light output oscillating like a breath. At its brightest, it is visible to the naked eye, pale red like a coal in the distance. At its dimmest, it vanishes entirely from view, but in infrared, Mira never disappears. Its surrounding dust shell continues to glow, even when the star's visible light fades. Infrared telescopes see Mira as a persistent source wrapped in warmth, a reminder that even when stars seem to vanish, they are still speaking, just in different tones. Let's shift our view now to planetary nebulae. These are not planets at all, but the glowing remnants of dead stars, shells of gas and dust, expelled in the final moments of a star's life. Inside the expanding cloud, a hot core remains, soon to become a white dwarf. To the eye, planetary nebulae are often teal-green, a result of doubly ionized oxygen emitting in the green part of the spectrum. But that's not their only color. They also emit in red from hydrogen, in blue from helium, in infrared from dust warmed by the central star. Depending on the filters used, the same nebula can appear green, crimson, or even violet. Is one more correct than another? No. Each is a different translation. Each shows what her specific wavelength, or set of wavelengths, reveals, and each whispers a different truth about what the nebula is made of. Even professional astronomers, when composing images for publication, must decide which wavelengths should be assigned. Which colors? Should infrared be shown as red? Should X-ray be blue or violet? Should radio waves be colored at all? These choices are often guided by aesthetic or didactic goals. Some maps are meant for public understanding. Others are meant for scientific comparison, but all of them are interpretations. They are not fictions, but neither are they neutral. They are again conversations. So when you look at a dusty star or a dusty galaxy and see that glow, know that you are not seeing the thing itself. You are seeing the history of its light. You are seeing what that light passed through, what it left behind, what it picked up. You are seeing the story of the journey, not just the source, and perhaps that's what makes astronomy so quietly profound. It's not just the study of objects, it's the study of paths, of shadows, of traces. We don't always get to see stars clearly. We rarely hear their full message, but we get echoes. And from those echoes, shaped by dust, filtered by perception and translated by instruments, we reconstruct the story. Not perfectly, but gently, honestly. So next, time someone asks you what color a star is, you might say, it depends on where you're looking from, on what tools you use, on what filters lie between you and the light. And maybe that's okay, because it means we are part of the process. We are not outside observers, we are participants in perception. And the stars, dusty as they are, seem to know this. They do not shout, they do not clarify, they whisper, and trust that someone will be listening. Every whisper fades eventually, not into silence, but into something softer still, a kind of hum that lingers, even after the source is gone. A dusty star may burn for millions or billions of years, but its light, once cast off, travels indefinitely. And while the star itself may grow cold, collapse, or fade entirely from view, the light it once released continues on, through clouds, through space, through time. And when that ancient light reaches us, changed by dust, curved by gravity, filtered through the narrow senses of our human eyes, or the glass and silicon sensors of our instruments, we interpret it, we color it, we try to understand. In this final section, we'll reflect on how we choose to see the light of the universe, and how, despite all our knowledge and tools, there remains a quiet truth, that every image we have of the universe is, in part, a story we're telling ourselves. Let's begin at a place where many of these stories start, the processing lab. Not the grand observatory dome beneath a canopy of stars, but the quiet, climate-controlled rooms where scientists and engineers take raw data, streams of numbers, signals, timestamps, energy counts, and turn them into images. Raw data, when first received from a telescope, doesn't look like a galaxy. It doesn't shimmer or spiral. It looks like noise, black and white dots, pixels of varying intensity scattered across a matrix. It takes calibration, the careful subtraction of noise and artifacts, corrections for detector sensitivity and exposure time, and sometimes the blending of multiple exposures across different filters to build an image. And even then the image is still incomplete, because most of the wavelengths we observe in modern astronomy are invisible. Ultraviolet, infrared, X-rays, gamma rays, sub-millimeter radio. To show these to the human eye, they must be assigned color. This is called false color imaging, though the term translated color may be more fitting. The idea is not to deceive, but to allow the invisible to become visible, and to preserve the relationships within the data. A filter that collects X-rays at 0.5 keV might be shown in blue. Another capturing softer X-rays at 0.2 keV might be green. Infrared emissions might be coded in red, yellow, or magenta. These assignments are chosen to highlight contrast, structure, and composition, to give shape to what would otherwise be shapeless. and in this process meaning emerges. Consider the famous image of the Eagle Nebula's pillars of creation taken by Hubble. The towering columns of gas and dust, glowing in green, brown and gold, look like cathedral spires reaching toward space. The colors are not what the human eye would see. They represent emission from oxygen, sulfur and hydrogen, coded into green, red and blue filters. But the emotion we feel when looking at the image, awe, curiosity, humility, is very real. The scientific image becomes, in a sense, a portrait, and the dusty stars within the nebula, whose light barely peeks out from behind the clouds, are not just points of data. They are characters, shaped by context, color and light. They become part of a visual narrative. And here's the gentle truth. That narrative changes depending on who's telling it. Astronomers process images for research, often in grayscale, or narrowband color. Artists and educators process images for public outreach, choosing palettes that feel intuitive or striking. A nebula may be presented in cool blues and violets for one audience, evoking calmness. The same object might be rendered in fiery orange for another, highlighting energy or turbulence. Neither is wrong. Both are real, in that they are rooted in data, shaped by light and crafted with intent, but both are interpretations, and so once again, we find ourselves listening not to the star itself, but to what we choose to hear. This becomes even more poignant in the case of blind astronomy, an emerging field where scientists and educators work to create non-visual experiences of astronomical data. Here, colors are replaced with sound. The brightness of a star might be rendered as volume, its color as pitch, its location as stereo direction. The dusty veil of a galaxy becomes a faint hiss or low hum. The glowing heart of a nebula becomes a rising melody. This is called data sonification, and it's not just for accessibility. It offers a new way of experiencing the universe, one that reminds us that color and image are not the only paths to understanding, and in some ways it returns astronomy to its roots. Before telescopes, before cameras, ancient sky watchers listened. They watched the patterns. They tracked the rhythm of the stars. They told stories, not of photons and spectra, but of hunters and rivers and sleeping lions. They saw the night sky not as data, but as meaning. And even now, with all our precision, we are still doing the same. We are building meaning from whispers. And what of the future? As telescopes grow more powerful, as they reach further into the past and detect fainter, colder light, our need to interpret, to visualize, to tell stories will only deepen. The James Webb Space Telescope, for instance, sees primarily in infrared. Its instruments detect the glow of dusty stars, of forming galaxies, of planetary systems wrapped in cold disks. The images we receive are raw, numerical arrays. To bring them to life, scientists assign colors to different filters. They choose hues that align with temperature, composition, or simply clarity. But each image is still a story, a whisper, filtered and colored and brought to your screen. And each dusty star within those images is a speaker, sending out light. That's been altered by dust, reddened by age, and finally caught by a distant listening eye. So we return to the question, why do dusty stars whisper different colors to different eyes? Because no one sees the universe exactly as it is. We see it as it arrives, changed by time, by matter, by our tools, by ourselves. And in this, there is no tragedy, only beauty. Because it means that the act of seeing is participatory. We shape what we understand. We decide how to listen. And we carry the whispers with us, Every dusty star you see through a telescope, on a screen, in a diagram, is a remnant of this shared experience, not just light from a distant object, but a message filtered by dust and space and time. Message that says, I am still here, I have traveled far, and now I rest in your gaze. And that perhaps is the softest conclusion of all, that dusty stars with all their filtered colors and veiled light do not ask to be understood completely. They only ask to be noticed, to be listened to be part of the story we tell when we look up.